So for the past few episodes, we have been looking at the sequences and series unit, and we've talked about sequences, and we've talked about the sum of sequences, but we haven't addressed what a series is. So that's just been looming over us for a while. So in this video, we're going to look at exactly what a series is, its definition, and we're going to look at a couple different common series, specifically the geometric series and the harmonic series. So I'm just going to jump right into it. Let's start looking at what a series is. So I have put here just the definition of a series. A series is a sum of an infinite number of terms. That is kind of bizarre. That's abstract. What the heck does it mean to sum an infinite number of things? So we kind of need to justify that to provide what that actually means. So here's an example. Let's first get an example out there. So we have 1/3 plus 1/9 plus 1/27. You can kind of see the pattern here. Every following term is 1/3 the size of the previous term. All right, so dot, dot, dot. This is kind of going to sum to something. A finite number for sure will sum to something, but what does it really mean to sum to an infinite number of things? All right, so this is what we're going to try to answer. All right, what does it mean to sum some sort of sequence? So what is the sum of I equals 1 of 1/3 times 1/3 to the I minus 1? If we let I go to infinity. This is where the idea of limits comes in. To do this, I want to look at one of Zeno's paradox. So Zeno had 3 paradoxes. I'm not sure the plural of paradox. Probably should look that up. But Zeno, a Greek philosopher, had a famous paradox where Achilles, so a little person, right? Cool. Achilles and a tortoise. This is my attempt at a tortoise. Were in a race, and Achilles let the tortoise start 100 meters further from it, or it doesn't really matter the distance. The tortoise gets a head start. So here's the starting point, and here's the race. And this is what Zeno was thinking. So Achilles is here, and the tortoise is here, and they're racing towards a finish line. And every time Achilles has traversed half the distance it is, so we'll call this Achilles 1. When Achilles has traversed the distance between it and the tortoise, half the distance, the tortoise has moved some distance, probably less than Achilles. All right, Achilles is going to be faster than the tortoise, but the tortoise has traversed some distance. All right, but now there is a distance between Achilles and the tortoise again. All right, and when it traverses half that distance, all right, this will be Achilles number 3. The tortoise has moved another amount of distance, all right, a little bit less. All right, but once again, when Achilles traverses half the distance between it and the tortoise, so this is Achilles now. All right, the tortoise has once again traversed the new distance. All right, turtle number 4. All right, and every single time Achilles traverses half the distance, the turtle has moved a little bit more. So what Zeno is saying is, will Achilles ever pass, or will Achilles ever catch up to this turtle? Every time it traverses some distance, the turtle traverses another distance, and it seems as though Achilles will never catch up. All right, but that's ridiculous. Achilles will eventually catch up and pass, right? And that's what I'm trying to make the point about, is that it is possible to, while there are infinite iterations here, there is a point at which Achilles will pass. So while we could do this an infinite amount of times, we will eventually catch up. So I can take a certain sequence of numbers, 1/2 plus 1/4 plus 1/8 plus dot, dot, dot. But with the logic here, while I am adding up an infinite amount of things, the situation's happening an infinite amount of times, there is a point at which we can say that this will sum to a specific number, or we are getting closer and closer to a specific number. And that's how we're going to define this. All right, 1/2 plus 1/4 plus 1/8, that is going to sum to something. Let's look at what it sums to. All right, so we have 1/2 plus 1/4 plus 1/8. All right, we want to look at what this thing sums to, starting at 1. All right, so what's the sequence here? The first term is 1/2, and our ratio between terms is 1/2, so I minus 1. All right, I could just write this as 1/2 I, but I'm going to write it like this. And we're looking at this as I sum an infinite amount of them. All right, so the way we do this is we look at what we call a sequence of partial sums. A sequence of partial sums. Right? And the answer is right there, partial sums. So what does that mean? All right, a sequence of partial sums. The first term in a sequence of partial sums is if I sum this with just 1-to-1. So we plug in 1, we get 1/2. Right? All right. The second term in this sequence of partial sums is if I take the partial sum of this infinite sum of 1 to 2. So we have 1/2 and we have 1/4. If you sum those things, you get 3/4. All right. So we call this S1. We call this S2, like we did before with A sub 1, A sub 2. We call this S sub 1, S sub 2, when we're dealing with a sequence of partial sums. All right. This, not a series, by the way. We're getting to what a series is. All right. The series is the sum. All right. The sequence of partial sums, 1/2, 3/4. The next term, 1/2 plus 1/4 plus 1/8. I believe it's going to be 7/8. All right. If I keep going, all right, I believe the next term is going to be 15/16. Right? And if you notice, this numerator is never going to be larger than the denominator. All right? Dot, dot, dot. All right? S2, S3, S4. This is a sequence of partial sums. All right? And what we say that this infinite series, this series sums to, is the limit of this thing. Right? What's the limit of the sequence of partial sums as n goes to infinity? Right, a little bit backwards, sorry. All right, this is what we say the series is. So what is it? All right, 1/2, 3/4, 7/8, 15/16. Can we write this as a sequence? All right. Determining whether a series is a number or not is a difficult task. And we're going to look at some basic ones that aren't as bad as they can be. All right, we'll leave calculus to help us solve the other ones. All right, but okay, so we have 1/2, 3/4, 7/8. What is that sequence? Well, we know what this thing sums to. Right? What does this thing sum to? Well, it sums to the first term. Right? What is that? The first term times 1 minus r to the n. R here is 1/2. All over 1 minus 1/2. Right? That is the sum of an arbitrary amount, and that's what we want. We want to look at 1/2, and then 3/4, 1/2 plus 1/4, and we want to look at 7/8, 1/2 plus 1/4 plus 1/8. Right? This is that term. Right? This is the nth term in this sequence of partial sums. All right, Sn. All right, so we want to look at the limit as n goes to infinity of 1/2 times 1 minus 1/2 to the n all over 1 minus 1/2. All right, what's the limit of that as n goes to infinity? All right, and that'll be our answer. Okay, so let's actually evaluate this limit. So 1 minus 1/2, that's 1/2. And then 1/2 divided by 1/2, that's 1. So this is equivalent to the limit as n goes to infinity of just 1 minus 1/2 to the n. And then what is the limit of this thing? Well, 1/2 to the n, that's getting infinitely small. All right, and we could do a proof that the limit of this is in fact 1, but the limit of this thing is 1. So what is the series? What does 1/2 plus 1/4 plus 1/8 plus ... equal? All right, it equals 1. All right, the way we define a sequence, the way we define a series, S equals, all right, A1 plus A2, plus A3 plus A4 plus, I'll stop there, plus ... All right, what does this sum to? All right, the way we define this is if the sequence of partial sums, the limit as n goes to infinity of the sequence of partial sums, keep on, S and S sub n are different. This is a sequence, this is a number. Right? If the limit as n goes to infinity of the sequence of partial sums exists, then we say, and it is L, then we say that the series converges. That's the buzzword. Converges to L and is L. All right. In other words, S is equal to L. All right. However, in red, if, and it's not really red, if the limit as n goes to infinity of the sequence of partial sums, not the series, the sequence of partial sums, if it does not exist, then we say the series diverges. All right, so what is a series? It's a number. What is that number? It is the limit of the sequence of partial sums of how that series is defined. Here's another geometric example. All right, so if I give you the series, and when you're presented with series, you're either given the sum or you're given the first several terms, and your job is to kind of determine what it is in summation notation. But let's say I gave you 3, then I give you 3/5, then I give you 3/25, then I give you 3/125, and I want to know what this thing sums up to. All right? The first thing you need to do is you need to figure out what it is in summation notation. Geometric series, geometric sequences, that's very easy. Right? This thing is equal to the sum of the first term times the constant ratio I minus 1. And we're looking at this from 1 to infinity. Right? So what is the nth term in the sequence of partial sums? All right, we know what that is. We don't know it for all sequences, but we do know it for geometric. We also know it for arithmetic. All right, 3 is the first term, and then we have 1 minus 1/5 to the n all over 1 minus 1/5. All right, and we just need to figure out what the limit of this thing is. So what does this thing equal? It equals the limit as n goes to infinity of this thing. If I write out the first sum, the second sum, the third sum, what is that sequence getting closer and closer to? All right, we can do that real quick. So this is going to be 4/5. That's going to be, what, 15/4? And then we have times 1 minus 1 over 5 to the n. This thing right here, as n gets bigger and bigger and bigger, goes to 0. So we have 15/4 times 1, which is 15/4. All right. So 3 plus 3 fifths plus 3 25ths plus 3 125ths plus forever using that rule will be getting infinitely close as you want to 15 fourths. So we say this thing equals 15 fourths. All right, here's another one. All right, how about the series 2 plus 2 plus 2 plus 2 plus dot, dot, dot. So what's 2 plus 2 plus 2 plus 2 plus 2 plus 2? Now you might immediately know, but this is the sequence. Sorry, we need to look at the sequence of partial sums. So what is this sum? This is just 2. We're adding it over and over and over again. All right, so this is I1 to infinity. We're adding 2, 2, 2, 2, 2. So what is the nth partial sum? So the first one's 2. The next one's 4. The next one's 6. The next one's 8. So this is just going to be 2n. All right, this sequence of partial sums is going to be, the first term is 2. And then if I set n to be 2, it's going to be 2 plus 2, which is 4. Then 2 plus 2 plus 2, which is 6. And I'm getting this. And then, so there's my rule. And the rule is really important to get because that allows you to confirm whether this converges to a number and that the series exists, or if it diverges. So the rule is 2n. This thing is equal to the limit as n goes to infinity of 2n. And this limit is immediately noticeable as infinity. So this series diverges, right? The limit is not a finite number. So 2 plus 2 plus 2 plus 2 does not sum to something specific. And that's kind of intuitive because if you choose a number, this will eventually get past it. If I say, hey, like 2 plus 2 plus 2, that's going to converge to 168. Right? If I go far enough out, I'm going to pass 168. Right? That's different for the previous sequences that I've been dealing with. All right, where is it? This one, 1/2, 1/4, 1/8. All right. If I say 2, this sequence will never get to 2. All right. So there is a number that we will eventually get to, which is in this case 1. In this case, we diverge. We never get to a specific number. Well, we get to whatever number you want. Let's look at every geometric series. So a geometric series, that means every term, so it's a series, right? But every term is going to be some ratio different from the previous term. So we have a, the next term is going to be a times that ratio. The next term is going to be a times that ratio twice, and so on and so forth. This is the series. And what is the sequence of partial sums? Well, this is geometric, so we can do that. S sub n is going to be a. Let me do this. So S1 is a. The next one is going to be a times 1 minus r over 1 minus r. The next term is going to be a times 1 minus r squared all over 1 minus r, and so on and so forth. Right? The nth term is a times 1 minus r to the n over 1 minus r. All right, so we need to find out, if I want to know what S is, what is S? Not the sequence of partial sums, but the what it is summing to, the series. It is the limit as n goes to infinity of what I had just written. So let's look at this thing for different values of r. You may already notice what matters to us, but it's the size of r in comparison to 1. So let's look at when r, or the absolute value of r, is less than 1. What's happening to this thing? All right. So here, the sequence of partial sums is, we want to look at the limit of this thing. the limit as n goes to infinity of a over 1 minus r, that's some number. All right, unless, of course, this will definitely be some number, sorry. And then this thing, if r is less than 1, all right, this term right here, no matter how close it is to 1, will eventually go to 0. Right? So this thing right here, 1 minus eventually 0 is going to be 1. So if r is less than 1 of a geometric series, the series will be the first term of the sequence within the series divided by 1 minus the ratio. All right, that's if r is less than 1. All right, if r is greater than 1, let me go ahead and do this in a different color. If r is greater than 1, all right, the series will be the limit as n goes to infinity of a over 1 minus r times 1 minus r to the n. All right, this is a number, all right, the first term divided by 1 minus the ratio, all right, but this thing right here, this thing is going to explode to infinity if r is bigger than 1, even at 1.001, right? If you make n large enough, infinitely large, that thing will eventually start to explode. Just think of an exponential graph. No matter what the base is, it will explode if it's bigger than 1. Right? So this thing is infinity, and the series, so it's actually improper to write that. The series diverges. All right? It converged here. And it diverges here. What if r is equal to 1? All right, this is going to be, well, this is just going to be the first term plus another term plus another term plus, and we already talked about this. This thing is going to diverge. It's going to no matter what number you choose, this will eventually surpass it. Right? And how about r equals, or sorry, I shouldn't have written absolute value there. Uh-oh. Let me go ahead and erase. Because what if r is equal to negative 1? And what you have here is a plus negative a plus negative a, and that is also going to diverge, right? You're going to have, in your sequence of partial sum, it's going to be, the first term is a, so Sn, you're going to have a, then you're going to have a plus negative a, which is 0, then you're going to have a, then you're going to have 0, and then you're going to just alternate. And we've already looked at these alternating sequences. They do not have a limit, right? You're going to, no matter what number you pick, if you determine this to be a real number, you cannot get within epsilon of it. All right, so this one also diverges. All right, what's the conclusion here? A geometric series converges to the number a divided by 1 minus r if the absolute value of r is less than 1. Otherwise, it diverges. Right? So when you're looking at a geometric series, what you care about is that ratio. If it's less than 1 and greater than negative 1, you're golden. If it's outside of that interval, you are out of luck. All right, that's enough of geometric. Let's go ahead and look at the, and I say the specifically, the harmonic series. Well, let's look at the sequence first, and then we'll talk about the series. So the series is just the sum of all the terms in the sequence. All right, so a sequence is harmonic. And I'm not saying the here on purpose. A sequence is harmonic if and only if the reciprocals are arithmetic. All right, so if I have some sort of sequence, let's go ahead and write a sub n. You have a1, comma, a2, comma, a3, right? If this is arithmetic, then the sequence, I'm going to call it a prime, 1 over a1, 1 over a2, 1 over a3, that is a harmonic sequence. A quick example, and then we'll do a quick problem, and then we'll move on to a harmonic series. But let's say I have, like, let's say 2, comma 3, and not 3. Let's do 5. Let's have a common difference of 3. 5, 8, 11, so on and so forth. If this is my sequence, all right, then my harmonic sequence, I'll call it B sub n, is going to be 1/2, 1/5, 1/8, 1/11, dot, dot, dot. And notice that the harmonic sequence is not arithmetic. All right, the distance between these two is not the same as the distance between these two. I'm not saying harmonic series sequences are arithmetic. They're just derived from an arithmetic sequence. All right. So with that said, the harmonic sequence. Let's look at that one. All right. So the harmonic sequence. We'll do this on the next page. All right. Here is the sequence 1, 2, 3, 4, 5. Right. The harmonic sequence is 1, 1/2, 1/3, 1/4, 1/5, so on and so forth. That is what we call the. We give it the title, the harmonic sequence. Get an I in there. Woo! All right, so we've been talking about series, and we did geometric. I didn't want to just do geometric. Let's look at the harmonic series, and that'll be the last thing we do. All right, so the harmonic series. All right, the harmonic series is the sum from I equals 1 to infinity. Right, and you have that first term. All right, so we're trying to write this a sub n, where a sub n is the harmonic sequence. All right, so we have 1 plus 1/2 plus 1/3 plus 1/4 plus so on and so forth. All right, so does this converge? Yay, happy. Or does this diverge? Sad. I guess it's up to you if converging versus diverging is bad or good. But I like when things converge. We can work with it. It's a number. Whereas this is just garbage. You throw it out. Sad face. So there's a very clever way to show whether this series, this harmonic series, converges or diverges. And it uses something really powerful called the comparison test. So what we do is we compare it to something smaller than it. Like if I can find a series that is smaller than every single one of these terms, but diverges, then this thing must also diverge. All right, what do I mean by that? Well, here's a very clever trick. All right, let's take another series. I'm going to call it series small. All right, and what I'm going to do is I'm going to take the number 1, bring the number 1/2 down, but I'm going to look at these two things. All right, 1/3 plus 1/4. That is bigger than 1/2. All right. More specifically, 1/3 is bigger than 1/4, so I can write this as 1/4 plus 1/4. All right. And this term right here is smaller than 1/3 plus 1/4. Similarly, I should have wrote some more terms. We have, let's go ahead and write 1/7 plus 1/8 plus dot, dot, dot. Right? I can rewrite this as 1/8 plus 1/8 plus 1/8 plus 1/8. All right? This thing is slightly bigger than this thing. All right? And notice what I've done here. I have, all right, this small sequence series is 1 plus 1/2 plus 1/4 is 1/2. Well, sorry, 1/4 plus 1/4 is 1/2. 1/8 plus 1/8 plus 1/8 plus 1/8 is 1/2. All right? And I can keep doing this for 1 over 9, 10, 11, and 12. 13, 14, 15, and 16. Right? I could have 8 1/16ths, which are all smaller summed than 1/9 through 1/16. So that's also going to be 1/2 plus dot, dot, dot. And look at this. This is 1/2 plus 1/2 plus 1/2 plus 1/2. This is a geometric series. Right? Let's ignore the 1, right? Let's say this is 1 plus the geometric series of I 1 to infinity of 1/2 times 1 to the I minus 1. Right? R is 1. That diverges. Right? 1 plus garbage is garbage. Right? The harmonic series diverges because it is bigger than another series that diverges. So I've done a lot in this video. We looked at, what did we look at? We looked at the definition of a series. It is the number that a sequence of partial sums goes towards as you take the limit towards infinity. All right, and then we looked at the sum of a geometric series, and then we looked at the sum of a harmonic series. We're just doing those two. You're going to have to live with that. We will look at more complicated ones when we are in calculus. All right. But those two rules are kind of doable with what we have so far, and the other ones require fairly intense proofs. So you'll do those later. All right. No need to do things now when you'll do them later. Right? If you learn everything now, there'll be nothing to learn later, and that'll be sad. With that said, I'm going to close this one up. There you go, series, intro to series, I guess I could say. We've now talked about sequences and series. So there you go. Have a good one.